Okay, the recording has started. Uh, so in today's video, we'll be talking about how you can play with large language models and OpenAI API. So that you can get to know how things work, what are different parameters that you can play with, how can you run large language models from Hugging Face on your local machine. So let me share my screen. Today's lecture is heavily inspired from a Hacker's Guide to Language Model. This is a public repo posted by one of the founders of Kaggle and Fast AI. You can find his videos on YouTube where he walks you through how to play around with different stuffs. So I have based my experimentation based on this repo. Now let's look at the things of experiments we have done. So firstly, we are installing packages, OpenAI, take token. This is for tokenization, transformers. This will allow us to access Hugging Face models, Torch, Accelerate, Bit and Byte, Auto GPTQ, optimum datasets, and so on. Now let's start with the first thing, that playing with a tokenizer. Tokenizing is nothing but representing letters in terms of number. So for that, we'll be using, so OpenAI has an open source model called Text DaVinci 03. So we'll be using the tokenizer of that model. A tokenizer has a list of vocabulary and the way a model needs the data. So each model will have a different tokenizer. So let's see how the tokenizer works. So we have a text which is today is quite cold. Once we tokenize it, then it is represented by the numbers like 888, 318, 2407, and so on. And when we decode the token, we are back with our original string. Today is quite cold. Now let's look at OpenAI API. Now OpenAI allows you to call GPT models via Python code. So this is what we have done. So firstly, we need to establish a client, an OpenAI client, pass it the OpenAI key, which the OpenAI key you'll have to generate, and it will be like $5, and it will last you for a really long time. Now, there are a couple of things which are required. Firstly, if you are telling system, system is basically what we are asking GPT to be, and then there is user in that prompt. The user is basically prompt which the user types in. So what we tell the system is that you are an abroad studies consultant large language model that is familiar with all requirements for applying to different universities present in USA, along with different visa requirements and restrictions. So we are asking ChatGPT to assume the consultant role. And after that, as a user, we are prompting them, what is the average GRE score required to get into SJSU Masters in Software Engineering program? And we want to keep the range as narrow as possible. So for that, we are saying keep the range as narrow as possible. And we ask it for chat creation and completion. So that means based on this, it will complete the text. Now you get a chat completion object as a return, and from that, when you extract the content, it says the average GRE score required for admission is roughly around where is it? Competitive range of GRE score for admission is around 310 and 320, and it also mentions that it is important to note that other than average GRE scores, there are other criterias and so on. And this is just we can see how many tokens. So our completion was 135 tokens, our prompt was 72 tokens, and the total number of tokens which we sent and received was 210. And now let's see if we had used GPT-3 model, how much did it cost us? GPT 3.5 to be precise, 3.5 tokens. So GPT 3.5 costs about $0.02 for every 1,000 tokens, and GPT-4 costs around $0.03 for every 1,000 tokens. By using GPT 3.5, we have a really low cost, and it would have been significantly higher if we had used GPT-4. Now, let's say the same conversation, I can add a follow-up. So one thing to note is when you send a follow-up question to the OpenAI, to any large language model, it gets the entire conversation back and not just the question. So in this, by playing with the reply which assistant gave, you can get different responses. So these two are same. We are asking GPT for the consultant role, same question, a summary of the question, the summary of the response which it gave us earlier. And from that response, we are asking that I have a score of 310 and 3 years of work experience. Based on this, recommend some good universities for software engineering program. And considering that, it recommended us 10 different universities for the same. Now, as you can see, we have like the message has to be sent in a particular format to ChatGPT. To make our lives easier, we have developed a function to help us do that. This is that function. It will just take the client object, the user is nothing but prompt, system prompt, model, and some keyword arguments, which this will come to the keyword arguments later when we are using the code interpreter. So we'll be basically developing our own code interpreter. Now, print response is basically a simple a function to print response, or else you have to do this nested thing over here. We are asking best universities for PhD in AI, specify, give us best universities. Now, let's say we want to try a mm, different system prompt. Till now, the ChatGPT was told to be abroad studies consultant. Now we are asking it to be a comedian LLM who is really good at sarcasms and roasts. When we ask, so we got the prompt, I really got done by my girlfriend on Valentine's Day. GPT responds by saying, "Well, congratulations on achieving a special level." It responds with a witty joke based on like it's a a dark humor and sarcastic joke, as we asked it to do. Now coming to the interesting part, code interpreter. So what we'll be doing in this code interpreter model is we'll be asking GPT for the code, and then we'll be running the code GPT gave locally to produce the output. So here we have a function multiply a and b. This will just take two numbers and multiply them. This function, other than the main function, this is where the string describing the function should be more important, as it will exactly tell GPT what it has to produce. Okay, and now GPT needs the function in a schema form. This is just a quick way you can get it in the schema form. I took this code from the notebook as I mentioned earlier, and we asked the GPT passing the client object our function, and we tell the system that you only have to use the function that I provide. And in the functions argument, I this is why we had the keyword arguments. And the functions argument when you pass we pass the our function schema. And GPT responds like, yeah, to call this function in to perform this multiplication, you would need to pass these two arguments. You can see that you need to pass a as 1024 and b as 2. Now let's call a function to call the function. So we are allowing only so we don't want any kind of function to work remotely. So we are saying that we have defined two functions. Only these two functions you are allowed to execute. The first function is multiply, and the second function is run Python code. This is a separate function like def run Python code. We'll come to it later. It's right below that. So here we are saying that from the response, we extract the function call saying which function to call. We check if that function is allowed to run. And if it is allowed to run, we instantiate that function and pass it the arguments as given to us by GPT. And we do that, we are able to get 2048, that is 1024 into. Now run Python code. Basically, this allows us to run any sort of Python code. Again, this code, you can go deep into this code, but the overview is pretty much same as above. So it's just, yeah, you can get details of this function from this link on how it works and everything. Yeah, so basically this allows us to run any Python code. So here we can say a is equals to 9 and b is equal, this is an example. Inside a string, I'm giving a is equal to 9, b is equal to 5, and a into b, and it is able to respond with 25. So yeah, now, yeah, now we ask it, okay, what is the integral of 2x when x ranges from 1 to 0? And we tell the system that use Python for the required computation. And we specify the run Python code as a function to it, and we specify the schema of the run Python code. Whatever is the response, we call it to the call function, which we spoke about earlier. And then it tells us that this is the code. And it also gives you the answer as well. It will ask you if you want to proceed with execution or no, and it will give you the answer. Now let's, instead of just throwing us the code, we want to run the code which it gave to us, right? So we'll do the same thing, integral 0 to 1, and we want to run it like we want a proper string. So we'll pass it the same, will give us the run Python code, we'll pass the function, and then we'll pass to the run Python code, we'll pass the context of answer. Answer is what we got earlier, the code which we need to run to get the integral value. And when you run it, you get the integral of 12x from 1 to 0 is equal to 6. So that is 12x squared by 2, so 6 and minus 0. Now, let's ask it for any other input, but let's still tell it to use Python for any computation. Let's ask it a fact-weight response, that is, what is the longest bone in the human body? And we ask it to use Python for any sort of computation. Since there is no computation, it will not use Python, but it will directly give us the response, which is wait. Yeah, the longest bone in the human body is the femur. Now coming to Hugging Face, so you have a bunch of open source and closed models on Hugging Face, which you can use and run locally to play around with ChatGPT. So you install the required packages. We are going to be working with Llama 2 models, specifically the 7 billion parameter one. Now, one key thing is this is the private repository, and you'll have to apply for access before you can work with it. Now, it shouldn't take more than an hour or two for you to get the access once you apply. It's so we'll instantiate that from the casual, we are loading the model, which is we are loading the pre-trained model. From that, we are also loading the tokenizer needed for the Llama 2 model. And we are saving everything as PyTorch and we'll be running everything on GPU. So that's why you'll see the return tensors as PT because we are using PyTorch, and you'll see 2 CUDA because we want to run stuff in the whole app. So once we tokenize, so this is the interesting thing. So right now I'm asking Llama 2 to complete the line. Every night in my dreams, I see you. This is a song from Titanic. So I'm expecting, I see you, I feel you. That is how I know you go on. So that's what I'm expecting. So we tokenize the input. Attention mask is basically just it tells you, should you consider a token? It tells the model, should it consider the token for predicting or no. Yeah, we have tokenized our input, and now we pass the tokens to to the model and run it on the GPU, and it takes around 5 seconds. Now, one thing I forgot to mention is when we are loading the model, we are loading the float values as 8-bit and not the complete 16-bit float value. This makes the computation faster and the model loading time much faster. The model running time faster. So we pass the model, yeah, and it takes about 5.32 seconds to get it running. And we are asking it only to generate 25 tokens. So this is 5.2 seconds when we are asking for 25 tokens. As the number of token increases, the time it takes will also increase. And when we decode the result generated by the model, it says every night in my dream, I see you, I feel you, I reach for you, I need you, I want you, I love you, I'm stuck on you. Close, but not the song which we are looking for. Now we are going to be working with Llama 2, but where all parameters will be in the form called torch p float 16. This is an optimized parameter where it can enable the model to run fast and also have the 16-bit float. The same thing again, we load the model, pass it the tokens, ask it to generate that. I know you, I see you, I feel you. That is how I know you'll always be close to me because every night in my dreams it got this part right, but yeah, you see the model overall, the performance was slightly better in terms of getting the correct context. But if you look at the runtime drastically decreased because we are using a much more optimized parameter storage method. Now there is a quantized version of the Llama 2 model. A quantized is basically it's a much more optimized version which can run even quicker than the B-Pro 16 one, where it has a 16-bit uh, it has the integers are stored as 4-bit, but it is internally represented as a 16-bit number. So it allows for a much efficient computation and storage. Now note this is 1.2 seconds, a large threshold. We pass the same thing, pass the model, pass the GPU, pass the tokens, ask it to produce the next line, decode it, and we get I feel you, and that is how I know you will always be close to me because the answer is pretty much the same. But if you look at the time, it is much less. We earlier had 1.25 and now we have 1.09 seconds. Quantized models are generally quicker models. Now we will look at the 13. Till now we are working with 7 billion parameter models. Now we'll look at the 13 billion quantized 30, Llama 2 with 13 billion parameter quantized model. You get the model, ask it to generate. This takes roughly 1.88 seconds, which is, you might think it is more than what we did earlier, but you have to consider the number of parameters involved have now almost doubled. We went from 7 billion parameters to 13 billion parameters. And the response we get is, I feel you, I talk to you, I share with you my deepest secrets and my darkest fear. This looks more like a love letter than the song. So far, we haven't mentioned to Lama that this is a song which we wanted to complete, so just keep that in mind. Now, yes, this is a function which basically takes a prompt and a model and will generate the text so that we don't write the same code again and again. Since I was running everything in the same instance, PyTorch doesn't have a good memory management. So after downloading one model, before you move on to downloading the next model, you need to release the GPU memory, basically the VRAM, so that you can load the next model. Because of that, I have this line of code over here. Now, there are Llama 2 models are further fine-tuned. So you have Beluga models, stable Beluga. It has 7 billion model. It is a model which is an instruction-tuned model based on Llama 2. So you are basically, instead of just you will be passing an instruction to the model and expecting a song. So as we saw in OpenAI, we tell the system what it is. So right now are telling system that your stable Beluga is an AI that follows instruction extremely well and can complete songs. Help as much as you can. Now each instruction fine-tuned model, they require prompt to be in certain format. That format you can find out on their Hugging Face model card. But the format for Beluga is user and assistant and system prompt in this manner. Whatever prompt we have, we'll convert it to this and then we'll pass it to the model for prediction. So we have the prompt, every night in my dream, I see you, I feel you. What comes next in this song? We have the system description, a prompt, and we are asking AI to produce something. And over here, you will be able to see assistant says, here's the complete song. Every night in my dreams, I see you crying in the rain. You look like an angel. You're acting like one. I have never done this before. It is love that you are feeling, or is it just cold heart? So I am not sure how familiar you are with songs, but these are like a mix of a lot of songs. This is the first song. This cold heart. Come on, Elton John. Everyone knows it. You look like an angel. Your skin makes me cry. That's from Creep. So it's a mix of multiple songs, not exactly what we wanted. Now there's another fine-tuned model called OpenORCA Platypus 2, which has 13 billion parameters. It's a quantized version. It is also instruction-tuned parameter, instruction-tuned Llama 2. So we'll see how we get around working with this. Now, as I said, each model has its own way of prompting. So for this, the method is the format is this. So we'll just write a new format to get convert prompts in that. And now we are asking it to complete the song. And it says, I see you in my dreams every night, and with each passing days, I feel you slipping away, an ocean apart, but always in my heart. Well, not exactly the song we are looking for, but it did fill in something. There is like some sort of, yeah, as the cell says, there is some hallucination, but we are expecting the song by Celine Dion. The model doesn't know we are expecting this song. Now, retrieval augmented generation. What happens here is we take the question that we have asked and then we try to search for a document that could help the model answer the question. Now, let's say we could give the lyrics for the song which we want to the model, and then ask the model to finish the lyrics. That lyrics document would be able to help the model if you assume. So that document will act as the context. So this is just some code to there is an API called OVH which allows you to get lyrics of any song. So we just ping it to get the lyrics of the song. My heart will go on. In my dreams, I see you, I feel you. That the correct lyrics. And then we convert it to a question answer form, pass it to the model, ask it to complete it. The model says, I feel you. That is how I know you. Go on. Far across the distance and spaces between us. That's the song which we are looking for, right? So yeah, right now we explicitly pass the model the correct context, the right lyrics. Now, let's say you're running an automation, you get a random list, and then you have to find, okay, you have a bunch of songs. How do you find out which is the best one? Like which document do you need to give to the model for context? For this, you have it's called finding the right context. So for this, we have a special model called BG small ENV1. So this basically generates embedding. And then you can, so what we'll do is we'll generate an embedding of the model, the embedding of a document, and we'll compare these two embeddings. And then whichever has, for wherever the similarity is greatest with respect to the prompt, sorry, we consider the embeddings of the prompt and of the song lyrics or any context which you're looking for. And wherever we have the highest similarity, we'll use that document as our context. So here we can see, okay, so I loaded the sentence transformer. This is it will basically going to generate an embedding. And just to test it out, I'm also going to get the lyrics of a song called Fix You from Coldplay. When you try your best, but you don't. Yeah. So yes, so what I'm going to do is I'm going to ask it to generate embeddings for the question, lyrics, the question and both my lyrics. And it generates embedding of size 384 for each of the songs. And then we generate the similarity between the embed and my prompt, my heart will go on lyrics, and my prompt and fix you. You can see my heart, my prompt, and my the actual lyrics, the actual song has a much greater similarity compared to the other song. So this embedding similarities helps us to decide which is the right context to be given for a particular prompt. Now this works when we have a couple of hundreds of document to go through, but in case if we have millions of documents, then what we have to do is we have to use something called a vector database where we'll already store all the embeddings and not generate them on the fly. Now, so far we have been running everything on the GPU. Now, there is a new version called Llama CCP, which allows us to run the Llama model on the CPU instead of GPU. So exploring that. So basically, you can go to Hugging Face and then you have to download this model from the file section. Let me show that to you. CCP Hugging Face. Go over here. Model. These are all the models that are made using that. Wait, actually, if I just go over here, yes, this is the main reference repository which I've used. So local, so, yeah, you go to the blog 27 chat GG repository, and over here you can go to the file section, and you have multiple instances of the models which you can download and use it to run Llama 2 on GPU. So you download the file, install this package, upload your downloaded model on your try, and then you can load it and run it on any problem. I asked it which is the closest galaxy to Milky Way, and it responded by saying Canis Major Dwarf Galaxy. Let's see if it's correct or no. Oh, it's the Andromeda Galaxy. But yeah, you shouldn't rely on large language models for fact-based tasks. This is just to show you just because LLM runs and give you a response doesn't mean it has to be factually correct. And then we have fine-tuning tasks. So right now we are running on the free GPU of a Colab. So we tried the Axolotl, the Exotel thing. So Exotel is basically a lightweight fine-tuning methods for large language models. You just change simple configuration and it allows you to fine-tune like couple of large language. They have a bunch of large language models that will allow you to easily fine-tune. So yeah, I tried installing it. Right now, though, we are running Python 3.10 on this notebook. I tried installing it, but there were a lot of dependency issues. So I tried to retrain the model using the Hugging Face method, which is like you create a trainer object, you embed your own the long way, and not this was the acceleron, it was the short way, and this is the long way. But yeah, I was able to get things running, but at one point I ended up having a out of memory error. As I said, the GPU is quite small and retraining requires a really big GPU. So to overcome this, we have a new notebook. If I open fine tuning with Accent. So in this notebook, which is also present in my repository, I have shown you how you can run it. So a couple of things, just to run this notebook, you would definitely need a Colab Pro. You would need a NVIDIA Ampere series GPU. This has been run on A100. It is about 13 Google credits per hour to run it. And the entire notebook takes about 1.5 hours to run. Now, as I mentioned earlier, when we were trying to run it in the previous notebook, we had an error because of Python 3.10 and some dependencies and so on. Even though the site says that it should work with 3.10, Colab environment by itself has a lot of other packages installed, so it was causing some problem. So to get things running, we create a new Python environment, specifically a Python 3.9 environment, and install the Acceleton on it and then run it. So firstly, I've just created a new Python environment. All you do is you follow this link. There's a really nice Kaggle which shows you how you can generate a new Acceleton environment. And by the end of it, you'll be able to see that we are at Python 3.9. So one thing is now we are working with this environment. We won't be able to run things directly in the cell. We'll have to run it as a shell script. Like you can have write a Python file and then run it as a shell script. So now Acceleton has a dependency where it requires a Python version greater than 3.9 and a PyTorch version greater than 2. I'm installing the version which is just more than point 0.2 so that we don't have a conflict error. And then you clone the Acceleton repo. You installed all the required dependencies from it, and then you're good to go. Now, Acceleton repo by itself has a lot of examples on how you can fine tune. So for this example, what we'll be doing is there is a good data set which has a bunch of SQL queries. So it has a prompt, a context, and an SQL queries. These three things. So it uses the prompt and the context to generate the SQL queries. We'll be using that to fine tuning the Llama 2 model with 7 billion parameters. Firstly, we explore the data set. The data set actually is present on Hugging Face. So SQL data, known Rohit. This is the SQL data present on Hugging Face. It is just this data. Now let me show you all the code which is there, which is being executed in the file explore data.py. These files which I'm about to show will be present in my GitHub repository. Okay, let's get to data. So what we are doing is we are just getting the data. We are loading the data set, printing the data set to see the structure and printing one of the individual input IDs in it. And if you look over here, that's what you have. We have a dataset dictionary that we have three features: context, answer, question, number of rows. We only have one split, that is the validation split, and so on. And now, as I mentioned earlier, Llama 2 is a private model. So for me to able to run anything, I need to be able to log into Hugging Face with my authorized ID. So I just logging into Hugging Face using the Hugging Face CLI tool. And then once we install Acceleton, we need to provide it a YAML file. A YAML file will basically tell it how it can run a particular code, how to retrain a model. So here we have passed it. So you can ignore all this. This is standard. You'll find it in the Acceleton documentation. What exactly this is. The main thing is this. This also you can find to a good extent in the GitHub Acceleton GitHub repository. It's from derived from one of the examples in the YouTube video with slight changes here and there. So the main changes over here is we have done is we are training on this validation split instead of the train split. We'll provide the context as context QA load 2, and we are setting evaluation sample packaging as. Now this SQL YAML file, you'll have to put it into your current working directory or anywhere. Just create this file anywhere and pass it the entire path. And this is how the file looks. So over here we are telling it the base model to use. What is the model type? So it is llama for casual llama, the tokenizer, where our data set is. So this is since it is we can pass it local address, but as of now, by default, it takes it as a repo name from dataset. So this is the dataset repo name on Hugging Face. We specify what is the context, what is the type of the dataset. So it's a context-based Q&A dataset. And since we do not have a train split, so we have to go with a load V2. That's what's specified on the website for Acceleratron. So that's what we are doing. We're saying the split is validation, and there is some issue with current version because of which you have to specify eval sample packaging as false, or you might run into some issues. And yeah, after that you run the script. You just upload your file in the current the SQL your TML file in any, or you can rename it to anything. Just upload it into your current working directory, and it should run just fine. And once the model is done running, actually one more thing, in this file, you specify where you want that model to be saved after it is done retraining. So we are specifying it. This is the location where we want the model to be saved. And just to be on the safe side, we are copying it one more place to prevent any problems. And then we have the testing fine-tuning model where we are fine-tuning the model. We are testing the model we just fine-tune. So this script looks like this. So you have a vector model, which basically takes the original model and your model to combine because it's staged in an efficient way, so to recreate and update all the weights accordingly. And then you upload the model to your system. And after that, you can use the model for making predictions. This is the same as you get the data, the format, and use the dot model to make the predictions. We passed it the context and it was able to generate the query for us. So that's the presentation from my side. Thank you.